to quantize the scalar free field by using functional integration method. So the free field, the classical free field, is just a mapping from space-time into R. This is space-time. Okay? And we used, in fact, the trick of going to Euclidean space in order to compute things more easily. So, in fact, space-time is M13, but if I'm considering Euclidean space, this would be R4. Okay? And the action for the free field in Euclidean space-time is just the functional of the field configuration, which is the integral over M of d4x 1/2 Steve of, well, let us write it in the standard way, d mu phi plus m squared over 2 phi squared, where d mu means simply d over d x mu, where x mu is a mu component, the component for the mu of x. So x is vector x mu equals 0 to 3. Okay. And basically what we have to compute are objects with the weight. So we have to compute functional integral of the form integral with some measure on the field that I will not detail exactly, but it's just a local Gaussian measure, times the exponential of minus 1 over h bar SE of phi. Okay? We have to compute things like that. And we were interested in particular in computing expectation value of products of the field at 2 different points. Let us call it x and y. So x and y are events in this Euclidean space-time. Okay? And we are interested in computing the expectation value with this kind of measure of this projector field. So it's a problem, if you want, of computing the expectation with this measure SE of phi of this object. So we compute the expectation value of this random variable, these products of two random variables, where phi is the random variables with a probability law distribution given by the exponential of minus 1 over h bar times the Euclidean action. So this is the Euclidean action. Okay, and we have seen from the example of quantum mechanics that this is an object defined in Euclidean space-time. So it's a function, in fact, and this will be a function of that I will rewrite. It's a function of x minus y by translational invariance. And we have seen that if I compute this in infinite dimensional Euclidean space-time, then I expect that this we shall recover by going from Euclidean to Minkowski space-time by a Wick rotation. We should recover, if the quantization procedure is correct, the expectation value in the vacuum state of the quantum theory. So the lowest energy state of the quantum theory of an object which is a time order product of phi x, phi y, when by a Wick rotation, I mean that here I have Euclidean vector. So let us write it, denote E, when I am dealing with vector in Euclidean space-time. Okay, so this is Euclidean space-time. And here x and y are vector in the physical Minkowski spacetime, and the relation between two is that xe is given by a vector when I have the first component of xe is the Euclidean time, and the remaining three components are the ordinary three components of the position vector in space, while x is a vector where the first component is time in Minkowski spacetime, and the three remaining components are the component of space vector. Okay, and the relation between t and tau and I is given by this picture I've drawn already several times, which is that I have, which is this picture, that here is t, here is tau in the complex plane, and therefore tau equal minus it, or if you prefer, t equal I tau. Okay? So, now we have computed, last time we have computed this object by using simply techniques of Gaussian integration. Or if you prefer, using the results, mathematical results about Gaussian random independent variables. And we have obtained the fact that this function g of x, okay, let us consider the, well, let us write this ze. I decide that z is simply xe minus ye. It is simply the Fourier transform. So the Fourier transform in Euclidean spacetime of the exponential of I, the scalar products of a k vector with an x vector, times 1 over k squared plus m squared. Okay? So it's a Fourier transform of a Lorentzian distribution in four-dimensional Euclidean space. Okay? And so I ended there, and it's an integral which is in fact convergent. It's a well-behaved integral. It's just the Fourier transform of this object. And if you open your math books or you compute this integral by yourself, you found that it is a function which is okay. You can extend it from four-dimensional space-time to, of course, d dimension easily. So instead of having Euclidean space-time to be R4, you consider that it's d, and therefore it means that you consider that you are in a Minkowski space-time with d minus 1 space dimension. Okay, and if you do that, this becomes, in fact, there is a factor 2 pi minus d over 2. It's a function of the modulus of the vector z divided by the mass of the field to the power 2 minus the dimension of space-time divided by 2. And then there is a function of the modulus of the vector z times the mass. And this function is nothing but a modified Bessel's function of with an index which is d minus 2 over 2. So k nu of z is a modified Bessel function that you will find in any good math books about special functions. Okay? So we shall come back later in this lecture about the properties of this function, because of course all the physics of the model is contained in the properties of this function. Okay, but for the moment let us just assume that we know what it is, and therefore we compute this object. Okay, so what remains to be shown is to check that quantization procedure is correct, is to check that when you go back from Euclidean space-time to Minkowski physical space-time, we recover the results of canonical quantization that you have computed with Kostya Zarembo in the previous lecture. So let us check that. In fact, it's quite easy. Okay, so here is the relation between a vector in Euclidean spacetime and a vector in Minkowski spacetime. Okay, here I must integrate over a vector k. So what is this vector k? In the Euclidean case, the vector k is a 4 vector, and its first component, let me call it k naught. So this vector, let me call it ke, to be sure that this is, this is of course a z, to be sure that in which space I'm working. So I'm computing this function in Euclidean space-time, and therefore the canonical momenta, if you want, this conjugate variables, is a vector also in Euclidean space-time. And this vector, let me call this its first component k naught, and then the remaining component, the component of a vector in 3 dimensions. Okay? So now, when I am going into, I want to make this change of variables. So I want to go from Euclidean variables into Minkowski space. Therefore, I expect that I will make this transformation, but if I make this transformation, you see that this factor, of course, what is ke times ze? It is simply k naught tau plus kx, if ze is tau x. Okay? And if I make this change of variables, tau becomes imaginary. Therefore, if k naught is real, this becomes something which is complex. It has an imaginary part, and it's a disaster when you do this integration, because you have exponential of I times something which has an imaginary part. So you have an exponential of something which is real and which can grow up at some infinity. So it's a problem. So, in fact, to solve this problem, to go from there to there, you have to simply use the rules of integration, of Cauchy integration in complex plane. Let us consider simply, let us assume that in this integral, okay, I integrate over the first component of the ke vector, because that's the important. So, for the moment, the others k are fixed. One can integrate later about them, but I first integrate over k naught. So, what is this integral over k naught? I have something which looks like d3k, and I won't care much about that. And then I have an integration over k naught over 2 pi. And I have an well, let me be sure. I put this exponential of I k times x outside the integral over dk naught over 2 pi. And here I have something which is exponential of I k naught, k naught times tau. And then I have a 1 over, what is this? This is, of course, k naught. What is ke squared? Ke squared is k naught squared plus k squared plus m squared. And okay, that's simply because in Euclidean space-time, ke squared is, let us write it like that, ke squared is simply k naught squared plus k squared. Okay? And so you see that this integral, I am integrating, of course, from minus infinity to plus infinity over k naught. And I am, so here is a plane. Here is a complex plane in k naught. So this is k naught, and this is the real part of k naught. This is a complex plane, C. And in fact, what I am doing is that I am integrating over from minus infinity to plus infinity over k naught. So this is the path of integration over the variables k naught. I'm integrating k naught over the real axis. You see? Okay. And this integral, in fact, is an integral. This function is a function which is an analytic function in k naught considered as a complex variable. So you may consider this integral of a real variable as a Cauchy integral along the real line of a complex variable. Okay. And these complex variables, it has poles. It has two poles somewhere in the complex plane in k naught, and of course those two poles are at k naught equal plus or minus I times square root of k squared plus m squared. So you see, these integrals has two poles, one here and one here. They are somewhere symmetric along the imaginary axis. Okay? So now I want to, so it's a bit messy. I want to now to make this Fick rotation. So I want to change tau into minus it. So I want, this means that I want to integrate, how to state that simply. I start from a theory where tau is real, and at the end, I end up, so I want to do this operation, you see. So, as usual, I made a mistake. So, when t is real, it means that tau is imaginary with a positive imaginary part. So, I made the usual mistakes. Tau is equal to plus it, and t is equal to minus I tau. Because you see that if t is imaginary with an imaginary negative part, then tau is positive. Okay? So I'm making this transformation in t. So let us represent it in the opposite way. Here is tau, and I want to perform this Fick rotation over the variables tau, so that the imaginary part of tau becomes the real time. Okay? So in order, in this equation, in order to make this operation so that this integral makes sense, what I have to do is that I have to rotate simultaneously by the opposite angle the path of integration over k naught. Because I want, if I want that k naught times tau is always real, if I rotate tau by an angle theta from 0 to pi over 2, okay, I have to rotate in the opposite way k naught by an angle minus theta, so that the scalar product, well, the product k naught by tau is always a real number. So when I perform this transformation, I look for this integral, and I want to compute this integral when now tau is imaginary, I have to make this transformation, and I have to rotate this path of integration in this direction. And at the end, when tau is imaginary, therefore I am computing the quantity for real time, then I end up with a contour of integration which is vertical. But since it is vertical, it is very close to the poles. But when you turn it like that, you realize that at the end you have a contour of integration which is something like that. You see, simply by deforming the contour, you have a vertical contour of integration which goes from up to down, so from plus I infinity to minus I infinity, but it is a bit left to the pole, to the upper pole, and a bit right to the lower pole. You see? Okay. So now let us make the change of variables and call these variables. Yes?
In that diagram, you show that target rotated clockwise. But
Yes.
to get to tau, you have to rotate t clockwise.
No, I am rotating. To go from Euclidean to real time to Euclidean time, I have to rotate t clockwise, yes? So to go back from Euclidean time to real time, I have to go anti-clockwise.
But it's telling smaller than 0.
No, this is the orientation of tau. So if I choose that tau is plus I t, when t has a negative imaginary part, so t is minus I times something positive, then tau is positive. You see? Okay, so this is orientation. This is t going from minus infinity to plus infinity, and this is tau going to minus infinity to plus infinity. You see? You have just to get a bit used to that, but it's okay. So once you do that, so what you have to do is that simply rename. Do the same thing, rename, change the variables by assuming that the imaginary part of k naught, I call it a frequency omega, with the relation that k naught equal minus I omega. Okay? So now this is omega. Omega is minus I infinity here and plus I infinity here. Omega is minus infinity when k naught is equal to plus I infinity, and omega is plus infinity when k naught is minus I infinity by this change of variables. And once I have done that, I end up with an integral that I will write it here, which is that. So this is the function g I wanted. Okay? So I end up, let us write it here because it's a bit crowded. I have that g now is integral over d3k over 2 pi to the power 3. And now I just make the change of variables. K naught equal minus I omega over 2 pi. So I get an integral from minus infinity to plus infinity of d omega over 2 pi. Now I have exponential of I omega t plus kx. Okay? And then, what do I have? K naught is minus I omega, so by the change of variables, I have a minus I. Okay? Now, what is the denominator? The denominator, K naught becomes minus omega squared. Okay? K plus m squared is m squared is still k plus m squared. I made no change of variables over the spatial component of the vector. And I am integrating over which contour? I am integrating over a contour over omega, which is just, well, if I think about in terms of omega in terms of k naught, it means simply that I have to rotate anti-clockwise this picture. So what is the path of integration? The path of integration in omega, where this is real part of omega and the imaginary part of omega. Now, if I make this, so I rotate this picture, what do I get? Now, the poles, I have two poles here. I have two poles at, of course, omega equal plus or minus square root of k squared plus m squared. Okay, but the contour of integration I've chosen is just a rotated contour like that. So the contour of integration is something like that. Okay. So I am integrating over this contour, in fact. This contour in red. Okay. And you see that, in fact, this means that, in fact, the pole here has a small imaginary part, and the pole here has a small positive imaginary part. So you can rewrite this simply as d3. So let us rewrite this as d4k over 2 pi to the power 4, because this is just the first component of a 4-dimensional vector k equal omega k, exponential of I k vector x, and minus I over minus omega squared plus, oh, and this is now, of course, well, let us write it like that, minus k squared plus m squared, and minus I epsilon plus in the standard prescription. Because you see that this means that this poles here has a small imaginary part, and this poles here has a small positive part, and I am integrating over the real momenta of the position. Okay. So you recover now this integral with this prescription of integration over the pole. And that's precisely the function gf of x, which is the Feynman propagator. You see? So I indeed recover the correct expression for this I was looking for. I recover the expectation value on the vacuum state of the theory of phi of, well, this was z, I'm sorry. In my notation, this was z. This was z. And this is, for instance, the time-ordered product of phi of z, phi of 0, because it's invariant per translation. You see? So by this simple trick of making a Wick rotation on time, like that, and making a counter Wick rotation on the momenta k naught, I'm sure that this integral, I'm doing an analytic continuation of this integral considered as a function of z, and I get the correct results. You see? Yes?
That inner product we have inside the exponential.
Yes. Yes.
Or
Here, what I define by kz is simply it's omega times, that's what I wrote before, it's omega times t plus k times x. Now, if you, here you have, it doesn't mind if it's an Euclidean or a Minkowski space, because in fact, the vector z is a vector with component x mu. So it's a, I never remember if it's a contravariant or covariant vector. I think it's a contravariant vector. Okay? And those vectors are, of course, Tx. Okay. Now, in my notation, what is the vector k? The vector k is a vector which is a covariant vector. And its components are omega and k. Okay? And therefore, what I'm calling here k, the scalar product of k of z, is k mu x mu. So the metric doesn't play a role here. It's the same expression if you are dealing with a Minkowski metric or an Euclidean metric. It's the same object. You see. So no dependence on the signature of the metric of space-time. See? But here you have a factor which depends on the signature of the metric. See? Because here, so you see, for instance, that this factor here, this minus omega squared plus k squared, now is, you can consider as it to be k squared because it's k mu, k nu, and h mu nu, where h mu nu is a metric minus 1, 1, 1, 1, 0, 0. It's the inverse of the tensor metric in Minkowski space. So this is also a scalar product, but here the metric intervenes. And here you have a factor which is in Euclidean metric 1. Here the factor is minus 1, minus I. Why is it so? Because in fact this integral is in fact this d4k times minus I is simply, you can write it as d4k square root of determinant of the tensor metric h mu nu, which is the standard covariant measure on the space of k. So you see, here I have been very cautious in doing things separating time components or frequency component and space component, but in fact this whole calculation can be done in a completely covariant way. So everything is, so this proves, this ensures, for instance, not only that we recover the Feynman propagator, but that all this procedure is invariant under Lorentz transformation. It's relativistically covariant, this kind of calculation, you see? Okay? Yes? Yes, because if, it's just a way to, you take, this is in the limit, like you can rewrite this integral where here you have no epsilon, but you integrate over a contour which goes a little bit like that. You can also represent it as an integral where you integrate over the complex contour, but simply in this expression has a pole slightly above and has a pole slightly below, because you see that this expression has two poles. One pole at omega equal square root of k squared plus m squared minus I, something positive but small. So a pole like here. And another pole which is minus square root of this, so it's here. And in the limit where this pole goes there and this pole goes there, you recover the same integral as this one. So it's just another way to rewrite this integral. Here I specify the contour. Here I change a little bit the contour so that the poles are away from the real axis. And then I take the limit where such that those poles come onto the real axis, but I keep track of where is the integration path. So that's something that you found in, that's the Feynman prescription of integrating over frequency, and that's the standard way it is presented. You see? Okay? Okay. So, I'm going a bit slowly, but I think that's important that you understand, that you recover the correct results of the quantum theory by functional integration. And now I will consider now the more general correlation function. So we start from the same object, and of course it's not enough to know the expectation value of the products of two field operators in the vacuum to know everything about the theory. So now we are interested into general what is called green functions or correlation functions for the free field. And that's something you have done already in the quantum field theory course, and here the same recipe appears. We are interested into computing, for instance, in the Euclidean field theory, some x1. This is an Euclidean vector, phi of xn, where this is an Euclidean vector, and by Wick rotation, we expect to get the vacuum expectation value in the vacuum of the theory, the vacuum state of the theory, of the time-ordered product of field operator phi of x1, phi of xn. Okay, so the question is, how do we compute by the same recipe such expectation value? Now, you have seen that there is a result which is called the Wick theorem, which states that for any Gaussian random variable with zero mean value, vanishing mean value, we have the result that a product of an expectation value of a product of such object can be written as decomposed into the product of expectation value of two variables. Okay, you have seen that in the tutorial. It's a simple consequence of, and let us apply this to this. So phi of x in Euclidean space is just complicated but a Gaussian random variable. So we know that the mean value of is equal to 0 simply by parity. You can change the sign of phi, so this is obviously 0 by parity. If you change phi into minus phi, the law doesn't change. And we have computed, we know the correlation function of two variables, of two fields. We have computed that. We know that it's h bar, this function g of x minus y, x1 minus x2, sorry, that we have computed. And now what we know is that, from that, we know that if we compute this object, phi of x1, phi of xn, we know that it is 0 if the number of field is odd, by the same argument of parity. And we know that if n is 2m is even, we know that it's just given by a sum over pairings, all possible pairings of the field of phi of x, some phi of x. So you make a pairing and you compute the expectation value, etc., of pairing. Okay, and you have here, of course, m equal n over 2 different pairs. And a bit of combinatorial show you that if you look at the number of possible pairings between 2m elements, you get factorial of 2m, namely n, divided by factorial of m times 2 to the power m. This is the number of pairings. Number of pairings. Okay? Yes? The result is valid, strictly speaking, if you consider real Gaussian random variables, it's valid in the Euclidean, but then you can make the analytic continuation. So this result is valid. In fact, this result is valid both in Euclidean space and in Minkowski space. Yes? Yes. You did it only for the two-point function? So you haven't done it in general? Okay. So I have to. Okay, so I have to explain that. Then. Okay, so let me. Okay, so then I think I will spend the main lectures. Okay, so let us. Okay. So. Okay, so I will consider a simple random variables. So I consider a random Gaussian variable, which I will consider it's a vector v, which is a collection of number v a equal 1 to some big number n. Okay, and the probability law, so the probability distribution for this vector is p of v equal up to a normalization by a factor z, exponential of minus 1/2 of VA, AAB, VB. Okay? So we have seen that this is just a normalization. So that, okay? And you have seen that, and that's a matrix, a symmetric matrix. Symmetric matrix, real, if you want, if you prefer. Okay, and what you have computed is that with this probability distribution, if you compute the expectation value of two VA, VA and VB, you get the matrix element AAB, where AAB is just the AB matrix component of the inverse of the matrix A. Okay, that you have seen. Okay, then now, if you want to compute more complicated objects like VA, VB, VC, VD, where A, B, C, and D are some component, then you can do the same thing, and you find that this is VA, VB times VC, VD plus VA, VC times VB, VD plus VA, VD times VB, VC. Okay? And in order to prove that, there is a very simple way to compute that, which consists in computing what is the expectation value of the exponential of something which I will call GA times VA, where GA is another vector. Okay, so GA is a fixed vector as a component of a fixed vector G. So you have a random vector you integrate over, it's a random variables. GA is a fixed vector, and I want to compute that. Okay? So if I want to compute that, it's easy. This is the integral over dv of exponential of gv minus 1/2 of VAV, if I use compact notation, divided by the integral over dv of exponential minus 1/2 of VAV. Okay? This is a compact notation VAV for this, and GV is a compact notation for the sum over the indices of GAVA. Okay? And now you make the change of variables. In this integral, I change variables. I decide that I can change variables and explain that V is equal to V prime plus A minus 1 G. Okay? Let me make this change of variables in the upper integral. And then I get that the upper integral is equal to integral dv prime exponential minus 1/2 of V prime A V prime, that's a simple calculation, times exponential of G 1/2 of G A minus 1 G. Okay? And I divide by always the same integral. AV. But this is the same integral as this one. Simply, I integrate over variables V prime here. Here I integrate over a variable V, but this is a dummy variable, so this integral is equal to this one, so I can cancel those. I get 1. So finally, I get that this expectation value is simply given by exponential of plus 1/2. I'm sorry, this is a bit. This is exponential of plus 1/2 GA A minus 1 AB GB. So that's the main result. Okay? You need. And once you have done that, you simply expand in powers of G this exponential to get the various. So expand to order 1 in G, you will compute the vacuum expectation, the expectation value of these variables. But this is an odd function. It's an even function of G, so there is no GA term, so this is equal to 0. Expand this to order GA GB. You get GA GB A minus 1 AB, so you get this result. Expand to third order, you get nothing. Expand to order 4, and you get on the right hand side this quantity, and on the left hand side this quantity. You see? Okay. So now this is a general result valid for any random variables and any probability distribution. So if we want to apply this to this scalar field, the random variables are the component phi of x of the field at the position x, and the matrix A minus 1 is just given by this variance. So I get this general results, which is known as the Wick theorem. So I think with Kostya-Zarembo, you have seen a derivation of the Wick theorem, namely this formula when computing these quantities in real time using method of canonical quantization. Here I derive exactly the same results. The fact that you can express expectation value in the vacuum of time-ordered products of products of an arbitrary number of fields in terms of the expectation value in the vacuum of time-ordered products of two fields by purely method of analysis and of Gaussian integration. So those are two versions of the same theorem, one using canonical quantization of the ordering of operator, etc., and one using functional integration, and therefore integration over random variables. You see? Yes? Pardon?
Where you've written down your pairings.
Yes.
So subscripts.
Oh, the subscript is as just that the subscripts are all possible subscripts which made pairing, because you see you can write them in a formal way, but it becomes a bit heavy. So I prefer to say that here I said this is the first, I take A, this is second, I decide here that it's B, here it's C, and here it's D. Simply those pairings those indices have to be different pairings and equivalent by permutation. Okay? So, oh, I don't think. Yes? Pardon? Pardon? Yes, these results will be true, in fact, for any free bosonic field theory. So as long as the field may have several components, for instance, it will be valid also for the Maxwell field in quantum electrodynamics. As long as the fields are, the action is a quadratic function of the field, which is true also in quantum electrodynamics. I would say quantum electrodynamics without fermions, so pure U1 gauge theory. The quantum theory is only photons. Okay? And or more complicated theories like a field with several components, it will be true. So it's a general result. General for bosonic. Okay. This result doesn't hold for fermionic fields. So for the Dirac theory, such a result doesn't hold because the Dirac fields in canonical quantization anti-commutes. So there is a version of Wick theorem, and we will see it, I hope, 2 lectures from now, well, probably 3. There is another version of Wick theorem, which is a slight modification of the Wick theorem, taking into account the fact that for fermionic fields, namely fields with spin 1/2, 3/2, etc., the fields operator anti-commute, and therefore you have to take into account these anti-commutation properties for fermionic field. But there is also a Wick theorem which is slightly twisted for fermions. Okay? Okay, so then perhaps it should yes?
The second line, it says that it's equal to the matrix AAD or A inverse of AAD.
Yes. So I'm sorry, what is your question exactly?
Yeah, but are those two things equal to the side?
Yeah, it's by a definition, you know. I'm just using in tensorial notation. So when the indices are up, I'm considering the components of the inverse matrix of A. So these are just tensor notation. So if you are familiar with the tensor notation, and if you pay attention to the fact that the indices are up or down, this is the inverse of this matrix. If you want to be sure that you are dealing either with the matrix or its inverse, it's better to keep this notation of A minus 1. Okay? Okay, so then, well, let us apply these results to this case. And So we are interested in computing the correlation function, or if you prefer, it's called also either the green function or the correlation function of the field. Namely, it will be something like phi of x1, phi of x2, phi of x3, phi of x4. What Wick theorem tells us is that this object is simply phi of x1, phi of x2, this function times phi of x3, phi of x4. This is the first term, plus phi of x1, phi of x3, this propagator times this propagator, phi of x2, phi of x4. And then the third choice is phi of x1, phi of x4 times the expectation value of phi of x2 times phi of x3. Okay, let me see if I made no mistakes. Yes. Okay. And there is a very useful graphical representation of these results, which is the first step into what representation of quantities in quantum field theory by the means of Feynman diagrams. And I think you have seen that. You have already seen Feynman diagrams representation in the quantum field theory course. If I represent this correlation function simply as a big blob with legs attached to each field operator. Okay, so this represents the correlation function. If you want, this is the green function. Okay, and if I decide that the single propagator here, so this will be a 4-point, it is called a 4-point green function. And if I represent, so what is the 2-point green function? The 2-point green function, x1, x2, so I will represent this by a green function, is simply the expectation value of phi of x1, phi of x2. And I represent it just by a line, x1, x2, which is called the propagator. Okay, that's the denomination. Then what is this 4-point green function? This is a 2-point green function. What is the 4-point green function? It's given by this term, and this term is represented by the product of the propagator between x1 and x2, so it is this object. Okay, so this little picture with 2 lines represent the products of those 2 propagators. The second term here represents, then I have 1 connected to 3. So I have 1, 3, and I have a propagator connecting to 4. And finally, I have these terms, which is 1 connected to 4 and 2 connected to 3. Okay? So this is the result expressed in terms of propagator, and this is the same results represented in terms of those propagators. Okay? So this is a graphical way to represent the pairings, and to each pairing is associated a propagator. Okay? And once you have done that, you can continue the same game, and for instance, you can compute correlation between 6 points, for instance. I don't think I will be courageous enough to draw everything, but if now I am considering the green function between 6 fields, okay, 1, 2, 3, 4, 5, 6. So this is a green 6-point green function, which represents the product of phi of x1, the expectation value of this 6 operator. Well, this will be given by these terms: 1 connected to 2, 3 connected to 4, 5 connected to 6, plus, and then you can start to connect. You decide to connect 1 with 3, for instance. 1 will be connected with 3. And you can decide to connect 2 with 4, and 5 with 6, plus, etc. And you consider all the possible pairings between the 2 points. And if you made no mistakes, you realize that there is indeed 15 such different pairings, and 15, if I made no mistakes, is equal to factorial 6 divided by factorial of 3 divided by 2 to the power 3, because this is 6 times 5 times 4 times factorial 3 divided by factorial 3 and divided by 4 times 2. So this is indeed 15. Okay. So of course, those numbers grow very quickly with the number of 6-point function. For n equals 4, for 8 fields, I forgot, but it's around, I think it's more than 100 or something like that. But still, this means that you can reduce the computation of those complicated correlation functions in terms of those simple objects. And that's the properties of any theory where there is no interactions, because the action has to be Gaussian. So there can be a kinetic term, a term which describes the propagation of the field, a mass term, but there cannot be any interaction between the particle of the theory. So no interaction. Okay? So, is it clear? Okay, so now I think I have, well, say 10 minutes to do what I wanted to do during the whole lecture. So I will just explain what I will do, what I intend to do next time, which is to go now, once we have the whole apparatus to study the free theory, can we use that to study the interacting theory? Because, of course, we are interested in theory where there are interactions between the particles, or coupling between the fields. If the universe was made of free fields, it wouldn't be very interesting. We won't be there to study it. Okay, so let us go back now from the free theory to the interacting theory. And let us see whether we can do something. So now I keep that, and I will be interested into, instead of considering the free field, I want to consider the interacting scalar field. Okay, so the scalar free field, in fact, describes a field where the quanta of the quanta are particles with spin equals 0 and a mass equal to m. Okay, and therefore there are bosons. And you have seen that in the quantum field theory 1 lecture. Okay, so what kind of interaction? What is the simplest interaction we can expect for particles which are bosons and which have no spins? Well, they do not carry charge. They are neutral. They are neutral. Okay? They don't carry any charge. So you cannot have any interaction involving the currents. You can couple it to the electromagnetic field. So, and you want an interaction which respects the principle of locality in space. So you cannot have interaction distance faster than light interaction. So you must have a local interaction between the particles. Okay? This interaction must be repulsive. Okay. Why is it repulsive? It is because if the interaction was attractive, those particles are bosons. And if you have an attractive interaction between bosons, all the bosons can be in the same quantum states. So the wave function of the boson, if you want, will collapse immediately. So if you have an attractive interaction between bosons, there is no ground state for a quantum theory like that, usually. You must have some kind of repulsive effect. So there is not such a problem for interaction between fermions, because you have between fermions, you have the Pauli principle, which stabilizes the vacuum of the theory. But for bosons, you must have only a repulsive interaction. So a local interaction is something where basically, if you have two bosons propagating like that, I make a small picture, they can only interact at a given point of space-time if they are at the same time, at the same place in space-time. I want them to be repelled by each other. So what is the only possible way to do that? It consists in adding in the Lagrangian a term which involves 4 fields. Yes? No, okay, it will be equivalent to our hardcore condition, but let us describe it in the language of fields, not of particles. So, you see, if I have an interaction where some kind of hardcore but an infinite with 0 radius. So simply, if the particles are exactly at the same point of space, then it costs energy for them. And therefore, the only way to describe such an interaction using fields is to add a term in phi 4 of x. Because you have 4 field operators, so you can have a field operator which annihilates the state of this particle and annihilate the state of the particles, and then create another state for the first particle and another state for the second particle. So you need at least 4 field operators to create a local interaction between bosons. Okay? Now, this interaction has to be repulsive, so it means that it has to cost energy. It increases the energy of the systems if you have several particles at the same point of time. So these terms, the coefficient here must be positive. This is the potential energy. So there must be a coupling constant G, with G positive, which will be the coupling constant. Coupling constant. Okay, so the Euclidean action, which will describe an interacting scalar field, we expect that it can be only of this form if we consider that it describes an interaction with 2 particles, which is the simplest case. Yes? Yes, in fact, you might have a phi cube term, because the phi cube terms will describe the fact that 2 particles may annihilate and becomes another particles. But you are right. You cannot have a conservation of number of particles, because you can create particles and antiparticles. And when you have a scalar neutral boson, the boson is its own antiparticles. But So you might have very well have a phi cube term, but okay. Let us. I want only to have a two-particle interaction. Okay, that's my choice. Yes.
Can a massive particle be antiparticle?
Can a massive particle be? Yes. 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 Very well. Nothing forbids that. Antiparticle is just the states, you know, an antiparticle of a particle. You have a states, a one-particle states. You apply a PT transformation, and you get the conjugate. You get the antiparticle. But for some quantum systems, you get the same states. And that's in particular the case for this one, because there are no charge. There is those particles has a very simple law of transformation under parity, because it has no spin, so you cannot change the spin by making a rotation or by 2 pi. So it has to be, it can only be its own antiparticle. There is no way to distinguish a particle with mass m from something which would be an antiparticle. Either there would be two kinds of different particles, and therefore there would be two fields. Okay? So it means, okay, so if I want local interaction, repulsive, involving two particles, and then I get only this term. Okay, so this is the Euclidean action for an interacting scalar field, and if you want to be sure, in real time, what will be the Euclidean action? It will be d for x. Then it will be d over dt of phi squared minus 1/2 of d over dx phi squared minus m squared over 2 phi squared minus g phi to the 4. Okay? By exactly the same argument. These terms is put in the potential energy term of the field. So this is the action in real time, so in Minkowski space, time, and this is the corresponding Euclidean action. Okay, and yes? 1/2? Oh, I'm sorry. It's just that. Yeah, thank you. Okay, otherwise it wouldn't have been Lorentz invariance. Okay, so the question is, can we quantize such a theory, or at least, if not quantizing exactly, compute quantities using with such a theory? Okay, and yes.
From this approach, that's clear quanta of the field.
Good question. I should have explained that too, but then I have to go back to the free field. Okay. So so let us end up here and I will treat this this action next time. Okay. So why is there quanta in the free field? To understand why there are particles in the free field formulation that I did, you have to go back to the two-point function. The two-point function is this object. Okay. Then, and we have seen that we can represent it as something like integral E4k over 2 pi 4 EIKX, and let us write it like that. So I am in Minkowski space, so I have a minus I have a minus k squared plus m squared minus I epsilon plus e to the minus I k y. Okay? If you see this, you see that there is a pole here. If k is equal to omega k, there is a pole at omega squared equal k squared plus m squared. See? So now, seeing that by this relation, omega corresponds more or less to the energy of the states. Okay? So you see that if you represent the structure of this function in the k and omega equals the energy of your systems, you have poles along here, and you have for negative energies something like that. So you see that you have a singularity in this formula along this this line, which is given by this equation: energy equal square root of I'm sorry, k. This is a vector k squared plus m squared. Okay, so this the singularity, this surface here, because we are in a surface. If we are in 3 dimensions, is called the mass shell. Okay, because it tells you that something is happening when the energy of a state here is the square root of the impulsion of the states plus a mass. Okay, so the fact that there is a pole here indicates that something is happening. When you have this condition between the energy and the impulsion. Okay, but now let us. I'm not sure I can explain that very quickly because I'm not completely familiar with that. But basically, you can think of this as really, those are the operators, this is the states. Let us insert the unity operator here. You know that in a quantum theory, the unity operator is the sum over the states of the theory of psi. And you can take the eigenstate of the Hamiltonian of the theory. Okay? So when I represent this like that, I can represent this as a sum over all the states of the theory. These terms will correspond to the matrix element between the states with momentum k. This will correspond to the expectation value between the states psi with momentum minus k, and this represents the amplitude of the propagation of the state. And the fact that there are poles tells you that the eigenstates of the Hamiltonian of the systems are states with energy E and impulsion k in space satisfying this relation. You see, so the fact that there are poles here only along the mass shell tell you that you have only, as states of the theory, eigenstates of the Hamiltonian, states which carry an energy E, which carry a momentum k with this relation. And what are such states? They can only be particles. So those are the particles of the theory. So if you look carefully at the meaning of the form of this form of the two-point function, you can deduce that the spectrum of the particle is only made out of particle with mass m. You see? Okay. So this explanation is a bit confusing, I agree. If you want to go into more details, you have to look at the what is called the Lehmann-Kellen representation of the two-point function in general quantum field theory, which gives you what is the relation in general between the structure of the two-point function and the spectrum of a theory. So I can come back later, but I have to prepare a bit more. But the fact that there are the quanta of the free field are particles of the theory with mass m can be seen from the analytic structure of the two-point function. So in canonical quantization, you start with states which are particles, first quantized particle, and then you do second quantization and you get this form for the two-point function. But what I'm trying to explain to you here is that you can do the opposite. You can compute the two-point function by a completely different procedure of quantization, here functional integral quantization, where there are nowhere particles. You never deal with particles. You only deal with fields. At the end, you get the same results, so this result for the two-point function. And from the analytic structure of the two-point function, you can deduce what is the spectrum of the theory. You see that the spectrum of the theory, which is a place where there are singularities in these quantities, occurs only on a mass shell, and it tells you that the spectrum of the theory is only made of particle states. Okay? It's not, I agree, it's not a proof, but one can discuss that a bit later if you are interested. And I might, if I discuss the reduction formula, I might treat that in full detail. Okay? Yeah. Sorry.